Next, service accounts. Now, so we're familiar with services in Jam. As I mentioned before, services are a bit like smart contracts. They have code, they have state. They have a few other bits, but let's have a look. Firstly, a service in Jam is not known by by some sort of hash or address. In Ethereum, it's known by a 20-byte account ID. If you go to like pallet contracts or whatever in Substrate, it's 32 bytes that it's known by. In Jam, it's just a 4-byte, 32-bit integer, right? Service index. This is basically to try and keep the data sizes down, because we're running kind of quite close to the limits in a few of these data pathways, in particular work reports getting into the chain. So we want to really keep the service size, these identifiers low. And by and large, we don't need a hash because the service creation is largely synchronous. So we can just basically assign integers without worrying too much about any collisions. We'll go into that. Will we go into that later? We might go into that later. Right. Delta is where we store all of our services, our service accounts. So Delta has all of the bits of data to do with each service. If you look in the yellow paper, what is stored in what is expressed by sigma as the chain state, that's in delta in the grey paper. It's a dictionary, that's what this D type is, that maps a service ID into an account. Blackboard A there is an account. Service account is a few things that if you're familiar with smart contract chains, you'll already be familiar with here. So it's a tuple of storage dictionary S. This is a key value pair. Just is the service's storage, maps keys to values. In our case, S maps hashes, 32-byte keys, to blobs, arbitrary sized values. This is a bit different to both Ethereum and the Substrate smart contract systems. In Ethereum, it's hashes to hashes, and in Substrate, it's blobs to blobs. In our case, it's hashes to blobs. Mainly because we don't allow enumeration, and therefore mapping blobs to blobs is equivalent to mapping hashes to blobs. We have pre-image lookup dictionaries, P and L. Now, these are a little complicated, so I'm going to skip over them for a second. We have the code hash C. That's easy enough. That's the hash of the code of this service. The balance, B. The gas limit for there are two gas limits. One of them is the gas limit when we do a transfer. And if we look a little forward, we also have the gas limit for accumulate. This again I will go into in more detail in a second. All right, so let's jump back. Jump back to P and L. So as I mentioned before, there is a service by which an on-chain facility by which services can request a particular hash's preimage to be available in the refine stage. So jumping back to this board, during the reactor core, when a particular service is inside the reactor core, it can say to JAM, I would really like hash X, the pre-image of hash X, to be available at some point in the future to my any times my refine code is going to run. When it does this, it basically specifies not merely the hash, but also the size of the pre-image, and it puts down a deposit that is relative to that size. So it pre-commits to the size of the pre-image as well as its hash, and it puts down a deposit. This is why in here we have both P, which is the dictionary of hashes to their pre-images, and L, which is basically which pre-images have been requested by this service. And it includes not just the hash, but also its length. We need to store its length because we need to know how much the deposit should be, and we need to disregard any pre-images if they do not have exactly that length. I mean, technically, if the pre-image is smaller than that length, it would be fine. But anyway, we require accuracy. This maps onto some time slots. The time slots are a little bit fiddly. We're going to get to them in a second.